My name is Biswa, and I'm a software engineer in Nutanix. So today we'll be talking about IASO. This is a system which automatically detects and mitigates a new class of failures we have seen in distributed storage services, which is commonly known as fail slow. But before I introduce IASO, we must understand fail slow itself. So more specifically, we would want to know what is fail slow, and is it even a significant enough problem to solve? Also, we would want to explore the problem space of these failures and find a solution which is stable and accurate. So let me try to explain fail slow by comparing it with one of the commonly seen or understood problem in distributed systems, fail stop. So in fail stop failures, we assume that whenever nodes in a cluster fail, they always fail completely. They shut down completely. However, we have seen that in many scenarios in complex systems, this assumption doesn't always hold. And there are these failure cases where hardware and software components are still functioning, but in much, much lower performance than intended. And that's what constitutes a fail slow failure. So let's take an example. In one of our production cluster of 3 nodes, we saw that the Ethernet interface's speed on one of the nodes had dropped from 10 gigabits per second to 100 megabits per second. Now later we diagnosed this, found out that this was because of a bad cable. However, during the failure interval, the services on the faulty node did not fully die. So they were just slow enough that our metadata service instances running on the healthy nodes started seeing timeouts from the metadata service instances on the slow node. So this caused the metadata service to be slow, which eventually cascaded to our data service, causing a severe drop in performance and a subsequent cluster outage. Now, given that this was like a 3-node scenario, we could easily drill down to the node which was actually slow. But if this would have been a bigger cluster of, let's say, 30 nodes, then this would have been a nightmare to find out the actual slow node here. So now that we have seen how a fail slow failure looks like, let's try to argue that these problems are indeed significant enough to solve. So fail slow problems are frequent. In fact, we did a study of all fail slow failures on our production systems. And this study was over a 7-month period where we studied a deployment pool of 39,000 nodes. And we saw 232 such incidents. And this figure shows the distribution of those failures over those months. And what we see is that there is at least one failure every day. The second thing is that these failures are also very severe. Now, this figure shows us the CDF of the time taken to root cause those failures. And what we see is that in the worst case, these failures can take even days to be fully resolved. Like someone needs to find out what the root cause is or what actually led to the failure, right? So how do we solve them? So we took a look at some of the characteristics of this problem. And the figure on the left shows us the result, right? So we tried to, what we found is that these failures are more frequent on these newly deployed nodes or younger nodes exhibiting the typical infant mortality kind of a pattern. So an intuitive solution here would have been to aggressively monitor failure-prone entities, like we would say that we would want to monitor network to take care of network faults, right? So that we can catch these failures early on, right? But we tried to dig a little deeper into the root causes of these failures, like what were causing these failures. And the table on the right is what shows us the result. What we saw is that there is no single major entity which was responsible for all these failures. In fact, there were 5 different categories and distinct subcauses within them. There are also these unconventional failure types like environment and human errors, which are even harder to monitor. Also, some of these root causes may be unknown upfront, which makes monitoring impossible. However, we did get a few key ideas. The first idea was that any such failure eventually bubbles up to an application level, causing a service to run slower. For example, there's a machine with a VM and the service S1 running in the VM. Now, if there is a bad disk and S1 is doing local I/O, then eventually S1's disk threads will get blocked and S1 will be slow as well. The second observation is that in any distributed storage service, usually the peer instances keep communicating with each other, For example, S2 and S3 may be forwarding IOs from the local clients which are meant for S1. So from 1 and 2, we have this intuition that a set of healthy peers of a service can then collectively identify a slow peer. And that's the fundamental idea behind ISO. So essentially clustering. And this figure shows on a high level ISO's architecture and solution. So we have these cluster of machines with VMs running on top of it and service instances of different services running in each of these VMs. What every instance does is to periodically publish a stable score for each of its other peer. By a stable score, I mean the performance of the other peers which this peer has seen. It publishes it to a database called the score DB. And periodically, there's a score analyzer which aggregates these scores per service. So we compare the peers among a service only within that service. And then we run it through an outlier detection algorithm. And if there is a fail-slow node, that pops up as an outlier. And that's the detection part at a high level. So once we have detected a fail-slow node, we still need to prevent the failure from spreading. What we need to do is to localize the problem so that the entire cluster as a whole is not affected. And that's the quarantining part, which also ISO does automatically. And then the last step is to notify the user who can then take a look into the root cause of the issue. And this is the only manual part which is there in ISO today. So to explain detection in more detail, I'll go through these following questions, right? So the first question is, what is the requirement on the stable scores, or what does a stable score even mean? And then the second thing is, once we have defined what a stable score is, what kind of algorithm will give us these stable scores? And then the third thing is, how do we cluster these scores to even find an outlier? So I'll answer the first question by using this example. Let's say we have this failure interval where a fault gradually increases in severity, and then it stays high for a while, and then it gradually decreases in severity. What we expect here is a function that maps to a 1 or a high when the fault is severe, and a 0 or a low when the fault is not. So let's say we have a score pattern like this. The problem with this score pattern is that it can map to both 1 and 0 when the fault is severe, and hence this is not even a function which we can use. What we expect here is a pattern like this, the line in purple, and we call that as a stable score pattern, so that when the fault remains severe, the scores given out are also higher. So the scores are essentially not flaky. And now we will see what kind of algorithm will give us such a stable score pattern. And to come to that, let's run through some of the unsuccessful attempts that we have had in our course of building ISO. In our first attempt, we tried to use the number of timeouts as a scoring metric. The problem with that, it gave us a bursty score pattern like this. And to emphasize, these are the timeouts between two peer servers. And why we got this bursty score pattern is because depending on the peer, because different peers, these peers are also heterogeneous. So the number of requests to a peer can vary, and so do the number of timeouts. To avoid that, next we try to use the ratio of the number of timeouts to the total number of responses from a peer, which is also equal to the total number of requests sent out to the peer. Unfortunately, this also did not give us a stable score pattern. Instead, what it gave us was chunks of spikes. And we found that this is because there are these tiny intervals when a peer may not receive any request. Hence, the ratio is effectively 0 for us. Also, another interesting thing to note here is that the spike on the right is slightly lower than the spike on the left. And that's because the degradation level, what we are talking about, can also fluctuate a little. For example, if there's a network packet loss scenario where the network packet loss varies between 10 to 15%. So given a constant number of requests, if the network packet loss is at 10%, the number of timeouts we see from a peer are less. So hence the ratio of the timeouts to the number of requests is less, right? So as the degradation level also varies, the ratio also varies. So essentially, we wanted an algorithm which is robust, not just across the fluctuation in the request pattern, but also which is robust across the fluctuation in the degradation level itself. And that's where we came to building ISO. And we built, to build IASO, we used a technique similar to what TCP uses in congestion avoidance, which is based on the principle of AIMD, or additive increase and multiplicative decrease. And we use this principle to create a stable score pattern. And that's the fundamental idea. And this figure shows us how we apply AIMD. So we start off with a similar timeout to the response ratio as previously, but instead of, and this is the left figure I'm talking about, but instead of discarding our previous history, we keep a history of 1. So every peer remembers the last score it has given out. In the figure we see that's the previous score. And we also have this upper bound, or the worst score a peer can get, and the lower bound. The idea then is to take the current timeout to the response ratio in the current round, and then either move that previous score up so that it eventually hits the upper bound, or down so that it hits 0. So as such, our calculate score algorithms look something like this. So it takes in 2 parameters, previous and timeout to the response ratio. So if we see that the timeout to the response ratio is 0, which means that the peer might be getting better and better, and then intuitively we would want to decrease the score for the peer, but we don't want to decrease it immediately to 0, because that would give us a flaky pattern. We want to gradually decrease it. So equation 1 represents the additive decrease part of our algorithm. So if you see, the second part of the equation is a constant. So we decrease it step by step until it hits 0. And if the timeout to the response ratio is non-zero, then which means that the peer is seeing some timeout. So you want to gradually increase or even exponentially increase the score so that it gets a bad score as quickly as possible. And then the equation 2 represents the multiplicative increase part of the algorithm. And we see that there is a variable called near threshold, which regulates the rate at which we increase that score, and it's proportional to the timeout to the response ratio. So if we take an example, let's say our previous score was 32, and we are seeing non-zero timeout to response ratios. Let's say in the first case, we see a timeout to response ratio of 0.1, then the score increases just fractionally, like 35.2, because we are seeing that the other peer is seeing some timeout, so we want to increase its score, but not exponentially. But if this peer is seeing a lot of timeout, for example, if the timeout to the response ratio is 1, so all the requests we are sending out to the peer are timing out, so we just increase the score exponentially, and it can even double to 64. And what we saw is that this algorithm did give us a stable score pattern like this, which matched the failure severity pattern, which aligned well with the failure severity interval. So now we have these stable scores. So how do we analyze these scores? So in our system, what we do is that every peer instance submits a score for each of its other peers every minute, and it publishes these scores to a score DB. The score DB, what it does is that it keeps a sliding window of scores. In our system, the sliding window of scores is essentially 10, and periodically it creates this mapping of a peer to the set of scores it has received within the sliding window. And then what it does is to take the 30th percentile score, and it calls it as a representative score for each peer. So now we have this map of each peer and a representative score for each peer. And then once it has the set of representative score for all the peers, it passes it through a clustering algorithm. We use a clustering algorithm like dbScan. And if there is a fail-slow node, it pops up as an outlier. So the intuition behind taking this 30th percentile score is that since it's a percentile, if this representative score itself is bad, which means that we have seen a majority of bad scores for that peer in that sliding window. For example, if we see the first figure, node 3 is receiving bad scores from all of its other peers, but it's not, for us, it has not yet received a majority of bad scores yet. But in the second figure, since the 30th percentile score is bad enough now, we can now label it as a fail-slow node. Now let's talk about how IASO has done in production. So IASO has been deployed now for over 3 years now. When we did the study, it was deployed for over 1.5 years, and our study was over like 7 months. What we saw is that IASO offers 2 significant benefits. The first one is that IASO bounds this failure detection time by a constant value. So it's a constant configurable value, and that constant configurable value is essentially that length of the sliding window. For us, the length of the sliding window is 10 minutes. So once a failure happens, In 10 minutes, we are able to detect the fail-slow failure and mitigate it. And the second thing is IASO is highly accurate. So it has this 96 point, because it's a heuristic-based algorithm, there were some false positives, but the false positive ratio, or the false positive rate is very low. So now that we talked about the detection part in detail, now let's jump to the second part. The second part is essentially that we have a fail-slow node, but we still want to localize the fail-slow node so that the failure does not spread to all of the other nodes in the system. And so to do that, IASO also supports these automatic policy-based mitigation techniques. Let's go over them as below. So on smaller clusters where we do not want to take down a fail-slow node, because the drastic thing which we can do here is to just convert this fail-slow failure into a fail-stop failure, just shut down everything, right? But in smaller cluster, it's very expensive. So what IASO supports is to take away leadership leases from the services on the fail-slow node. And that's important because we know that these leaders in the distributed system act as like coordination points. And so if the leader is slow, the whole service as a whole is slow. But if we take away the leadership leases from the service instances on the slow node, then at least this cluster as a whole is stable. The cons of this approach, however, are that the node still remains as part of the cluster. However, it's still useful if the failure itself does not persist for long. Let's say it's a failure which we can easily find and fix, and so we can just restore the node back to normal, so we don't have to go through the expensive process of taking it out and then adding it back. Although in bigger clusters where we do not want the cluster to be running in a degraded state, IASO does support policies like shutting down the VM itself or shutting down the slow node itself. Obviously, the cons here are that it will trigger a VM rebalancing or a service reconfiguration. And then the last part is the resolution of these fail-slow failure, where IASO alerts the user that, oh, okay, there's a fail-slow failure, and someone needs to take a look into it. This part is manual, but two important things to note here are that by this time, IASO has pinpointed the actual node which is slow. So anyone taking a look at the cluster does not need to look at all the nodes in the cluster. They just need to look at this one specific node. And then the second thing is, by this time, IASO has also localized the problem. So the cluster as a whole is not affected. Yeah, so to conclude, fail-slow failures are severe problems which need to be addressed correctly. The correctness part is very important. And IASO does that with a very low false positive rate of 3.7%. And also, the study of fail-slow failures that we have done in our production clusters over 7 months, we have collected that data set and made it public, so do check it out. Yeah. Thank you.
Okay, any questions?
Nelson Liao from FutureWay. I have a quick question. Actually, your model is really based upon the monitoring of each node of the clusters with a homogeneous type of configuration. Is that right?
Homogeneous? No, it can be heterogeneous. I think that ratio is what makes, yeah. So if it is heterogeneous and we are using timeouts, that's where we saw that in a heterogeneous configuration, using just raw timeouts fail because the number of timeouts to different peers can vary, okay. Right? And so it does not support ISO supports heterogeneous configurations as well. Yes.
Okay. A second question is actually I don't see. I see that you're using the adjustment score, which is very similar to a kind of like a sliding window things to phase out the to reduce the spikes, right?
The adjustment score is not to reduce the spike itself because the spike reduction is taken care by that AIMD approach we talked about. Right. The adjustment score is more like we are seeing these timeouts, but at what point do we cut over and say that, oh, this node is slow? So let's say our timeouts, let's say we just wait for 1 minute or even lower than that, let's say a few seconds, right? So then we would have these even in flaky scenarios where we are seeing a small fault for only a few seconds, which just disappears after that, we'll still label the cluster, the node as slow. And the reason we wait for a longer period, like 10 minutes, so that essentially to answer your question, that sliding window is the amount of time which we wait before we label it. And that's important because the mitigation techniques can be drastic. We can take down the node, right?
Okay.
So we want to be more conservative.
Okay. The last question. Actually, in your very first slide, you marked the cost of those fail slow.
Yeah.
Could be coming from some intrinsic permanent type of causes like configuration, environmental type of thing.
Yes, yes.
How do you counter this? I mean, how do you have the IASO to be able to detect this type of intrinsic failure, the permanent failure, not a temporary?
So what we are saying is that there can be a lower level permanent failure, but eventually it bubbles up to make the application slower. So what we are interested in is the application permanently failed or slow, right? So if the permanent failure of a disk, let's say, permanently stops or the application is in a crash loop, for example, right? So, or the application has, for some reason, has shut down, that the permanent failure at the disk level has manifested as a permanent failure at the application level, then it's anyway a fail-stop failure. And we have mitigation technique, like if there is a fail-stop failure, we just fail over to some other node, like there's leader re-election protocols and all, which take care of electing a different leader and all those things, right? But in this cases where there is a permanent failure at a disk level, but it manifests as a slow application or a slow service instance, right? So those are the kind of things we catch. So at the root cause, yes, it can be a permanent or a slow disk.
Okay.
Yeah.
Thank you.
Yeah.
Last question, okay.
Abhinav Dugaldel. I'm curious about false positives. What kind of false positives do you see? What are the reasons? And there are things like GC could be running on a node, and that means that maybe it's a performance bottleneck. It's not really a fail slow scenario.
Yes. Actually, yeah, GC is a good point, because the thing is, if it is slow enough, right? So what we say is that it is persistently slow, so that if the GC is running for a long period of time, and let's say the service instance also hosts the leader, right? So for that amount of time, you would still want to like fail over the leader somewhere else. So you are saying that, and that's where when I was talking about those sliding window, that sliding window is a configurable parameter to say that this is an amount of time period to which I can tolerate, and after that I'll just declare that node to be slow. So if the GC is running for an hour, or let's say like a long period of time, right, more than our window, then we will label it as slow, so that we can still mitigate and fail over the leader to some other instance, for example. Yeah.
Okay, got it. Just one last thing. Just curious, have you looked at any other anomaly detection algorithms or any other clustering algorithms?
So any other clustering? Oh, you mean apart from DBScan?
Apart from DBScan.
Yeah. So we didn't spend much time in the clustering algorithm itself, because I think that was more like a standard. We can just use any standard clustering algorithm. There's no logic as such in the clustering algorithm itself. I think the two important things are this ability to generate stable scores, because we want it to accurately align with the failure interval. Right. I think that was one of the major concerns.
Okay, got it. Thank you.
Yes.
Okay, let's thank our speaker again. If you have other questions, you can, of course, talk to the speaker offline. Okay.